Rutherford's idea of what the nucleus is. So Thomson's model was proven incomplete with the Geiger and Marsden gold foil experiment. In other words, as the gold foil experiment uncovered some new things, we found out that the Thomson model was not quite correct. The repulsion was unable to account for the small angle of scattering. And I think you remember the one that we're talking about where the nucleus, where the gold foil particles are actually being fired like this at the nucleus, and we end up with these small angles of scattering where they're just deflected a little bit. How do we account for that with the Thomson model? We know that some of them came back like this, but most of them went straight through, right? So what we're wondering about are these small angles of scattering. In other words, this one down here and this one up here. How does it account for those? Well, the angle of scattering was only possible if the alpha particle could penetrate the atom itself, or get inside of that electron radius and get close to the very concentrated center of it. It would give us the correct amount of force to repel the alpha particle using our Coulomb force here. This is kind of what we were just describing just now, at those small angles of scattering like this. So what we ended up with is that the structure of matter had to change. So we started off with electrons, with photons, with protons, and then neutrons. And then, as we were talking about in the last section, we were talking about there were neutrinos that were starting to be found, or the small neutrons, or the small particles. And so we end up building these particle accelerators that produce high-speed collisions of particles. And these accelerators use electrical fields and magnetic fields to accelerate these particles close to the speed of light. So by 1950, there were hundreds of smaller particles that had been discovered, and more than 30,000 in operation today. So these atom smashers, or these particle accelerators, these 30,000 particle accelerators that are in operation all around the world, are finding new particles. And one of the things we want to define is an elementary particle. So an elementary particle is a particle not made of any smaller components. It has the most basic constituents of matter, or in other words, these elementary particles are the most basic pieces of matter. So what we do is we have high speeds in these particle accelerators, and most new particles are highly unstable, and they only exist for a very short amount of time. And these hundreds of new particles are known to exist. So in a situation like this, you can see over here, so we end up with a proton that's moving, and one maybe that's stationary, or one that's maybe even moving the opposite direction before the collision. When we smash them together, you'll notice we end up with two protons, but we also have this pion over here, or a neutral pion. So the collision produces an entirely new particle called the neutral pion, and the particle lives for about this many seconds before it decays into two gamma ray photons, so it turns into light afterwards. Since the pion didn't exist before the collision, it was created from part of the incident proton's energy. So the energy actually creates these particles. We also have these things called bubble chambers, where these bubble chambers are where we can smash particles together. These were some of the early particle detectors, and bubble chambers have these small bits of water vapor inside of them, and it allows us to see trails like this through the water vapor. And depending on the direction of spin, and of course the radius of spin, we can see how much energy they have, what charges they have, and if we know their speeds, then we can actually find their masses with the momentum. So this particle adventure that we have is going to be making up reality. And so we have forces, we've got particles, and we're going to make this thing called reality. And this is really where your standard model comes in. So you guys did a little bit of standard model matching, and I think that looks something like this. And so your standard model is here, and you have some particles down here. Hopefully you've put them all together into a standard model. It looks something like this. And so what we have here is we have some quarks in purple, we've got some leptons in green, and we've got some gauge bosons in red over here, or these are force carriers or force mediators is what we can call them. And then of course we have Higgs over here, which is a scalar boson, which we'll get into that in just a minute. You can add that to your grid. I think the grid in your notes needs to have a Higgs added to it. So there are three major parts, those exchange particles, like we were talking about, these bosons over here. The quarks are in purple, and the leptons are in green. We've got some forces here. The electromagnetism, gravity, strong and weak forces. And when we talk about the number of bosons, these are the gauge bosons from over here, our red bosons. The number of bosons, you'll notice there are 3 for the weak nuclear force, but each of the others has 1 boson. That the boson name for electromagnetism is a photon, for gravity is the graviton, and of course this one has not been discovered as of this video. The strong nuclear force is mitigated by a gluon, and the weak nuclear force has the 3 different particles, W+, W-, and the Z boson. And the masses of these, take a look at the masses of these zeros, and then weak nuclear force has a large mass. We'll study these in more detail in a little bit. We could have a positive and a negative 1 or 0 for those weak bosons. And then, of course, what does it act upon? This is sort of expanding what we did with our fundamental forces table. So are they fundamental or are they composite? Remember, we made a list of those different particles. I think that's the one that's on the next page. So quarks and leptons are fundamental particles. These two here, they are not thought to be composed of any smaller particles. So hadrons, such as protons and neutrons, are all composed of quarks. So when we talk about hadrons, they are the smaller parts of them are called quarks. So of course we have hadrons that are broken up into mesons, baryons, and then we have nuclei. And nuclei are just what we were talking about before as baryons. Hadrons, such as protons and neutrons, are all composed of quarks, and these matter particles are referred to as fermions. So we have a particle tree here, and I think you guys filled this out for homework. Take a minute to fill it in. If you haven't yet, go ahead and pause the video if you'd like to. For particle physics, the particles are really going to be leptons or hadrons. There are 6 different kinds of leptons. They're fundamental with no internal structure, and there are hundreds of hadrons. They have an internal structure made up of smaller particles and are therefore not elementary. The particles that make up those hadrons are called quarks. So we've got 3 elementary particles here: exchange particles, quarks, and leptons. The first one we want to look at are exchange particles. So in order to understand these particles, we'll take a closer look at those fundamental forces. Remember when we talked about the relative strength? If strong is 1, then gravity becomes very weak. The weak force is slightly stronger than that, and electromagnetic slightly stronger. So for exchange particles then, we've got strong, electromagnetic, weak, and gravity. And here's another table showing the strengths, the range of them. One of the things you want to notice about the range of the strong and the weak forces here, the range is very, very small. So 0.1% of the diameter of a proton and the diameter of a medium-sized nucleus. So the weak force is actually a smaller range than the strong force. This is a smaller range than the diameter of a proton, or 0.1% of the diameter of a proton. And of course those particles again. So we've got strong, electromagnetic, weak, and gravity, and those exchange particles that go along with it. Let's take a closer look at the strong force. Exchange particle is a gluon. It affects the color of the quarks. It's massless, has a strength of 1. Its range is really the diameter of a nucleus. It's involved in short-range nucleon-nucleon interactions, and it interacts with other gluons and quarks. So you can fill in the boxes here for each of these. Electromagnetic force is here, looking at the photon as the exchange particle. It affects all charged particles. Once again, it's massless. Its strength is 1/137th of the strong force. Its range is infinite. It's involved in the Coulomb force and magnetic force, and interacts with charged particles. And this is not a Feynman diagram yet, but this is. We'll start looking at Feynman diagrams shortly. The weak force is what we should look at next. Looking at exchange particles, those bosons, W plus, W minus, and Z bosons, which is neutral. It affects quarks and leptons. The masses are around 80.4 and 91.2 giga electron volts, which is really big, 80 times as massive as a proton. So these things are much bigger than a proton in mass, which might seem a little strange. The strength of them, the range, and they're involved in changing one quark flavor into another quark flavor. How do they interact? Well, they are intermediate bosons. In other words, they are in between particles. So in a case like this, where we have a down quark turning into an up quark, it gives off a W minus boson, and this neutrino then, or this electron-flavored neutrino, it absorbs the W minus boson, and it turns into an electron. And these are the relative charges that we'll look at here in just a moment. What about gravity? Exchange particle is a graviton. Here you can see a picture of a graviton. We don't actually know what they look like. It affects all masses. So the graviton doesn't have any mass itself. Its strength is very weak, but its range is infinite. It's involved in mass attraction, and it's similar to photon interactions of the electromagnetic force. That's what we think it's going to be like. On the next page, then, we have, first, before we get into that next page, we want to look at the data booklet reference here, that you don't have to memorize these particles. They're here for you, and you can tell which forces they are associated with. The Higgs boson. What we want to do is to add the Higgs boson to our list. It was the missing link that was late to be experimentally verified, and it was about 2012 when they first thought that they verified it, and it was a little bit later when they finally had the data that said yes, it was what they were finding. So the Higgs has to do with mass. It's the exchange particle that makes it possible for mass to exist. Without it, standard model disintegrates mathematically, and it's responsible for the mass of all particles in the standard model. It may be the first step in discovering dark matter, which is a substance that's believed to account for around 5/6 of the matter in the universe, and dark matter is undetectable since it does not interact with electromagnetic radiation. Xiaolan Wu was a Chinese-American particle physicist, and she's a very influential in making contributions towards the discovery of the J particle, which provided experimental evidence to the existence of the charm quark. So as we start getting into different particles like this, we want to highlight some of the people that have actually done this. And there's quite a bit of diversity in the scientists that have created or discovered some of these particles. The second one we want to look at are quarks. So quarks were first proposed by Murray Gell-Mann and George Zweig in 1964, and there are 6 different flavors. So in this case, we're going to call the different types flavors. So we've got the up quark, we've got the charm quark, and we've got the top quark. It used to be called truth, but right now we're just calling it top. Once again, it's sort of symmetrical on the other side. We have the down quarks, which go with the up quarks. We've got the strange quark that goes with the charm quark. And we've got the bottom quark that goes with the top. Truth and beauty, either way. The top quarks over here have a charge of plus 2/3 of that fundamental charge, or what we're calling the fundamental charge here. And this would be like a proton, this fundamental charge. The down, strange, and bottom all have a charge of negative 1/3 of that fundamental charge. And so what we can do is we can put these particles together to make up hadrons. And those hadrons are the familiar ones, like our protons and neutrons. So these are going to be making up our protons and neutrons. There are antiparticles of each quark called antiquarks as well, which is anti-up, anti-charm, anti-top, anti-down, anti-strange, and anti-bottom. There is no uncle bottom. This is Murray Gell-Mann and George Zwig here at the LHC when it was being built back in the day, and there are a couple articles here that you can check out as well if you'd like to. I'll put those in the description. Hadrons. Let's define some of these things. So a particle made out of quarks is a hadron, and there are two types of hadrons. We can have baryons, which are made up of 3 quarks, or 3 antiquarks make up an antibaryon, or we can call them mesons, and you might recognize this from your particle tree. It's made up of 2 quarks, 1 quark and 1 antiquark. So we've got baryons and mesons. So quarks only occur in hadrons, which means they only exist in a baryon or a meson, and they're never found as a single quark, which is kind of strange. But once again, from the data booklet, you'll notice that all these items are here for you. You don't have to actually memorize them. So which baryon would be made up of these quarks? Up, up, and down. So let's see if you can do a quick calculation of what the charge of an up, up, and a down would be. What we would do is we would take this up and give it a 2/3 and a 2/3 plus a negative 1/3 e. That's going to give us a +1. So if this particle has a +1 charge, which particle is it? Go ahead and pause it and see if you can figure it out before I give you the answer. Let's look. This up, up, and down particle here is going to be a proton. And of course the flavors are given here. Which baryon would be made of an up, up, and a down? That's your proton. What about an up, down, down? See if you can do this one. Pause the video. That's going to be your neutron. What about baryons and mesons? Well, those are also hadrons. So you want to have your particle tree open when we're doing some of these things, because hadrons are baryons, which are made up of 3, and mesons, which are made up of 2. So over here we can see baryons, over here we can see mesons, and they all fall under the category of hadrons. So the IB will assume that you know the quark composition of protons and neutrons along with their antiparticles. So the proton and neutron are the only ones we really have to memorize, and that's up, up, down, or it's down, down, up. If we're talking about the neutron, that's the one that has the downs in it. The proton has the ups in it. Mesons look like this, which are really 2 quarks, but there's always 1 quark and 1 antiquark bound together by the strong force. So we could call this one a positive pion, and it's consisting of an up quark and an anti-down quark. Always a regular quark and an antiquark. Are mesons hadrons? You know the answer to that one? Yes, they are. Pions are here too. Pions are mesons that consist of an up quark. So what they've done is they've made little families of these different mesons. And these types of mesons that have the up quark or an anti-up quark are all called pions. So we've got a positive pion, a negative pion, and you don't need to necessarily know these, but one of the things we do want you to do is to recognize that they exist. Are pions hadrons? of course. Here are some other examples. We have a neutral pion that can decay into many other hadrons. So this neutral pion then in the center can decay into all these other hadrons. These are kaons over here. So moving along any line, only one quark or antiquark will change. So what we end up with is a whole bunch of different particles that can come from this neutral pion. Now, antiparticles have the same mass but are opposite in all other properties. When it comes to antiparticles, remember antiparticles have the same mass but are opposite with all other properties. So, for instance, if we have a particle P, the antiparticle to particle P minus can be P plus, or a particle P's antiparticle can be P with a bar over it, or we could just call it P bar. If we have hydrogen here, we've got a proton with a plus charge, an electron with a minus charge here, or a negative charge. We can have antiproton, which is just H bar, and the antiproton would have a negative charge, and the electron with a positive charge we know is called a positron. So this could be hydrogen and antihydrogen. When particles and antiparticles interact with each other, what we can say is that they annihilate each other, or they become energy. The mass is converted into energy in the form of photons, and the mass goes away. So it can be calculated by taking the total minimum energy of 2 photons, or these pieces of light that are coming out, and the rest energy of the particle plus the rest energy of the antiparticle. So one of these would be the antiparticle, one would be the particle, and so we would take the rest energy of the first particle and the rest energy of the antiparticle and set it equal to the total minimum energy of 2 photons. So we could do this using our Planck constant and the minimum frequency of those pieces of light, and then 2 times the mass of those particle and antiparticles. That would be our HF minimum is equal to the energy, or the original energy of those particles, the minimum energy for each photon. So annihilation and pair production are kind of opposites of each other. In other words, the opposite of annihilation is pair production. In pair production, a photon is converted into a matter particle and an antimatter particle. So if we have a photon coming in, then we could have an antiparticle and a particle. And we can calculate the rest energy in pair production the same way we did with annihilation, except only one photon is turning into 2 particles in this case. So what we have is our HF minimum of this light that's coming in, and 2 times the mass, or the energy in mega electron volts. The minimum energy of the photon, the rest energy of the particle, and the rest energy of the other particle. Now let's take a look at quarks. Quarks have electric charge and also a property called baryon number, and this is going to help us with conservation. So every quark has a baryon number of 1/3. So every antiquark then has a baryon number of -1/3. In all reactions, electric charge and baryon number are conserved. So this is kind of getting us into our conservation laws already. So to find baryon number of hadrons formed by quarks, we add the individual baryon numbers. So let's say we have an up, a charm, and a top baryon. We're going to take the charge of the up, the charm, and the top baryon. That would be a baryon number of 1, or a positive 1. A UD, or a U anti-D, up anti-down meson, then would have a charge of 1/3 and a -1/3, which would give a baryon number of 0. Because, is this a baryon? No, this is actually a meson. So there are hundreds of hadrons and many symbols. Here are a few more. We can talk about pions, etas, chions are all mesons. And we can talk about lambdas, chis, omegas, deltas are all baryons. So we can discuss a few decays here, or really just two so far. What we have is we have two different decays here, and what I want to do is to just exemplify the differences between them. Over here, we've got our delta particle, and it decays into a proton and a pion. In this case, it's a negative pion. This delta is a neutral delta particle. Over here, we've got our lambda, our neutral lambda particle, and that decays into a proton and a negative pion as well. Now, the baryon number is +1 on both sides. In other words, we have a baryon here and we have a baryon here. And of course, this pion is a meson, so it does not give us a baryon number. The lambda is a baryon, proton is a baryon, and once again, this is a meson. This decay, in this case, takes about 10 to the minus 25 seconds, whereas this decay takes about 10 to the minus 10 seconds. So when we look at these decays together in the laboratory, they definitely look different. In other words, this large times difference suggests that there are different interactions. In other words, shorter lifetimes, something like this over here, is a strong nuclear interaction. And longer lifetimes is going to be a weak nuclear interaction. So strong nuclear interactions are really indicative of short lifespans or short decay times, whereas longer decay times are associated with weak nuclear interactions. Strangeness. Well, strangeness is strange. Strangeness is a property that we initially needed to explain the behavior of our massive particles such as kaons and hyperons. These particles are created in pairs and collisions and were thought to be strange because they have surprisingly long lifetimes of 10 to the minus 10 seconds. Now that's relatively long. It's still fairly short in our human lifetimes, instead of the expected 10 to the minus 23. A strange quark has a strangeness of -1, so this is a little bit different than what we've seen before. And a strange antiquark has a strangeness of +1, so this is strange in the fact that the regular particle has a negative charge on it. This property of strangeness is conserved when strange particles are created, but it's not conserved when they subsequently decay. So let's look at one of these particles and look at its decay here. So we have this lambda particle, and in strong interactions, the charge, baryon number, and strangeness are conserved, but in weak interactions, the charge and baryon number are conserved, but strangeness is not. So this is a property of a weak interaction. So you have to be careful when they ask you questions about weak interactions and strangeness. So let's take an example here. Determine the charge of the hyperon, whose quark content is down strange. State whether this hadron is a baryon or a meson. So let's see here. We've got our table from the data booklet. We've got our charges and our quarks here. And what we're looking for is determine the charge of the hyperon. And what we have here is we have down, and strange. Can you use this table to find it? Go ahead and pause. So we have down, and strange. It's all -1. So state whether this is a hadron or a baryon. Well, we've got 3 quarks here, so we know that it has a baryon of 1/3 as well. So since a hadron is made of 3 quarks, it is a baryon. We could also add up the baryon numbers as 1/3, 1/3, and 1/3 to give us 1 baryon. Let's do a second example. Read it over, pause. So state the quark content of the antiparticle and the pi plus meson with an up anti-down content, sort of over here. We can take our chart again, the quark content of the antiparticle of the positive pion. Well, since the antiparticle is found by replacing all of the particles with their antiparticles, the antiparticle would consist of an anti-up and a down quark. Does that make sense? So state the quark content of the antiparticle of this meson. It's just the opposite of this one. Let's try a third example. Go ahead and read it over. Pause the video. This one says state the baryon number, the strangeness, and electric charge of the hadron anti-strange, anti-strange, anti-strange. So we're looking for the baryon number, the strangeness number, and the electric charge of this hadron. So we're going to use our table again. So in this case, since the hadron is made of 3 antiquarks, we've got anti-strange. So here's our strange. The baryon number is -1/3 because it's the opposite of this one. -1/3 and -1/3, which is a -1 baryon, which means it's an anti-baryon. The strangeness in this case, if we have an anti-strange particle, remember a regular strange particle is negative, but an anti-strange particle is positive. So the strangeness number for this one is anti-strange gives us a +1/3, a +1/3, and a +1, a +1, a +1, and a +1. So the strangeness of this is +3 overall. The electric charge, can we find the electric charge of this one? So anti-strange, that one's going to be a +1/3, +1/3, and +1/3. We have an electric charge of 1. Kaons are a group of mesons consisting of an up or a down quark or an antiquark with a strangeness quark. So the two factors are that it's either up or down along with a strangeness, and this is called a kaon. There's also a thing called quark color charge or quantum chromodynamics. So QCD is short for quantum chromodynamics, and we're going to get further into this idea of color. In other words, the overall color or flavor of a baryon must be colorless. So all quarks inside of a baryon must be different colors. And so this is the rule for the flavors. So we have a red, we have a green, we have a blue. And all of these colors together are very much like light, where they overall make a white light, or colorless. You can think of it that way. Similarly, the overall color or flavor of a meson must also be colorless. Mesons consist of 1 quark and 1 antiquark. Overall, the color of a meson is colorless. In the case of a meson, if I have a red quark, then the antiquark would be anti-red. Let's take a look at Pauli exclusion principle and spin. Here we've got our increasing electron energy, and we've got different shells that we might recognize as the SP, and then of course D and F are the others that we look at when we talk about electron energy levels. In this case, the scientists had discovered that there are 2 electrons in the first energy level of the atom, which was not allowed by the Pauli exclusion principle. So what they ended up doing is they invented the property of spin, so that these 2 could be in the same state together or in the same energy level, but what would happen is they would be moving in opposite directions, or really, they didn't really even specify. They just had a new property, very much like color, that they called spin. So if we have one here that's going one direction, then we'll have the other having another property, a different property called spin, where it's going the opposite direction. The atoms had different spin and therefore can occupy the same space. So all hadrons are made of 6 flavors of quarks, or out of these 6 flavors of quarks, plus 6 antiquarks. They each have a spin of 1/2, so that a particle with a spin of 1 or 0 with mesons must be made of 2 quarks, and particles with a spin of 1/2 or 1.5 must be made of 3 quarks. So they're going to be talking about the spin of these particles, the spin of different baryons and the spin of different mesons. This would be a spin of 1, spin of 0, and of course this baryon would be a spin of 3/2, This one would be a spin of 1 over 2, or 1 to 2 and 3 to 2. So the Pauli exclusion principle also applies to quarks in a baryon. No two quarks can have all of the same quantum numbers inside of a baryon. So this applies to the color charge, like we were talking about just a moment ago. At quantum chromodynamics, the quarks are allowed to have the same flavor as long as they have a different color. So just like we saw with the strangeness or the lambda neutral particle, they can all be strangeness or anti-strangeness as long as they all have different colors. So for color charge, remember, we've got to have different colors of the up, different colors of the down, different colors of charm, and so on and so forth. And of course we have to have different colors of our strong force gluons as well. So for color charge, they propose that quarks can have 3 color charges like this. We just talked about this one. This type of charge was called color because of certain combinations of quark colors would be neutral, in the sense that they would that 3 ordinary colors can yield a white or a neutral color, and the only particles that are color neutral can actually exist. So since this omega negative particle has 3 strange quarks, the only way that all 3 can exist in a baryon is because of color charge. So this is another property that we have that needs to be satisfied for conservation. Now the cool thing is that quarks can change. Quark flavors, up, down, strange, and charm, top and bottom, can all be changed by a weak interaction. So quark colors inside of one baryon can change due to the emission or absorption of gluons. And as one quark changes, the other must change to keep the overall color charge colorless. So it would look something like this, where a down particle or a down quark would turn into an up quark, and it would emit a particle here. And this up quark would then turn into a different color of up quark, and it would emit a particle here. So the weak force is this dotted line here, and that mediates quark flavor change. And that could be something like a W- boson. But the strong force mediates quark color change. And do you guys remember the particle that mediates the strong force? That's right, it's the gluon. So an example of quark flavor change by the weak force is what you're seeing over here. This is another Feynman diagram where we have a B quark or a bottom quark, and it's turning into a charm quark. And as it turns into a charm quark, you'll notice at the same time it emits a weak force boson. Now you can see the squiggly line that I have here. You can either use this squiggly line or you can use this dotted line. Either one really works for the weak force, and that weak force then turns into a down quark and an anti-up quark. So we'll talk about these arrows and the direction of these arrows here in just a moment. But what we're talking about is that the charm quark, while also giving off a W- boson, is also decaying. The bottom quark is decaying into the charm and the W- boson. This decay then produces a down quark and an anti-up quark. Quarks are held together by gluons, so the strong force binds the quarks together in a baryon or a meson. So the strong force is the one that's holding all of these together. And the gluons are strong force carriers. The gluons carry color charge. So we can have a blue quark turn into a red quark no matter what the flavor is, whether it's an up or a down. Then the color can actually change, and it gives off this curlicue of a gluon. Here you can see the same thing happening. So strong force and strong nuclear force are what we need to differentiate now. That the strong nuclear force is a residual force that comes from the strong force that binds the quarks together in a baryon. So these are two definitions here that we really need to show how are they working, or where do they come from. So that's what we're going to do first. Quarks exchange gluons, and here we have some quarks exchanging gluons that are now bound together in a baryon. And these strong force carriers, or these gluons, are the ones that are holding it together. This is the strong force. So when we're talking about whether it's the strong nuclear force or the strong force, It's the strong force that holds the quarks together. So let's make sure we can differentiate that. And this is really what it kind of looks like, is that this quark is exchanging gluons with this quark is exchanging gluons with this quark, and so on and so forth. And that's what we call the strong force. That's gluon or color force in this case. So let's say we have another baryon here. This other baryon we know is going to be attracted to this one through what we think of as the strong force. But this is going to be our strong nuclear force. So in other words, here's the strong force inside of the baryon. The strong nuclear force is the one that holds these baryons together on the outside. And that's actually done with pion exchange. So pions are exchanged between baryons, and that's the strong nuclear force that binds the nucleus together. This is a quick data booklet reference from 7.3. The last piece then is to look at leptons. We've looked at exchange particles so far, quarks. Let's look at leptons next. There are 6 flavors of leptons, and hopefully you've heard of this first lepton before. Do you guys know this one? When I say you guys, I mean all of y'all. This is our electron. We've got a muon and we've got a tauon, or a tau. We've also got neutrinos that come with this one. Do you guys remember the neutrinos? Well, they come in different flavors too, and they're sort of families together. This is the electron neutrino. This is the muon neutrino. And I bet you can guess what this one is. It's the tau neutrino. Move those down a little bit. The leptons are grouped into 3 generations or families. So here's one. Here's the middle one here. Here's the bottom one. The electron flavor and the electron neutrino are the first generation. Then we've got the second generation and the third generation. The leptons on the left have a charge of -1, while the neutrinos are neutral and also are close to massless. So you can think of them a little bit like this, where you've got your electron neutrino and your electron. You've got your tau neutrino and your tau particle, and you've got your muon particle and your muon neutrino, whereas the muon is the biggest or the largest. We've also got antileptons. So remember, we have not just tau, but we have a positive tau now. So we have electron, positron. The positron is the antiparticle of the electron. We've got the muon and we've got the anti-muon. We've got the tau and we've got the anti-tau. And of course we've got antiparticles of all the neutrinos as well. So electron neutrino, electron antineutrino, muon neutrino, muon antineutrino, tau neutrino, or tau antineutrino. Leptons are those fundamental particles like we were talking about with quarks, where you can't get any smaller. The fundamental particles don't have any constituent parts. In other words, we can't go any smaller than them, or at least we believe we don't, or we can't. They're called leptons as they're considered to be lightweights, although the muon is as massive as a meson, and the tau has a greater mass than a gold atom. So these are some strange things that we found out later on. Leptons do not feel the strong force, they only feel the weak force, which is like beta minus decay, and the electromagnetic force. So with each lepton, there is an associated neutrino, and neutrinos only feel the weak force as they have no charge. The only stable lepton is the electron. The muon and the tau are highly unstable and have very short lifetimes. Here's a total of 12 leptons. We just saw those. Here are some particles of the standard model links. This is taken right from a wiki page, so you can check out any of these particles from the standard model.